There is a rock face in Namibia that should not exist, not in the way that something is rare, or surprising, or hard to explain, in the way that if you understand what you are looking at, the rock in front of you is telling you something that the rest of your education insists cannot be true. The man standing in front of it in the summer of 1998 was a geologist named Paul Hoffman. He had spent decades reading rocks the way other people read documents, slowly, carefully, with the understanding that stone does not lie, but that it does not always tell you what you want to hear. What the rock in front of him was saying was this: there had been glaciers here. Not on a mountain, not at high altitude where ice is expected and unremarkable. Here, at sea level, in sediment layers that the ancient magnetic record placed within 20 degrees of the equator, within what should have been 700 million years ago. A warm tropical sea, glaciers at the equator. Hoffman had seen glacial deposits before. He knew what they looked like. The scratched and grooved surfaces where ice had dragged rock across rock. The jumbled sediment full of stones too large and too varied to have arrived any other way. The drop stones, individual boulders dropped into fine ocean sediment from the belly of a melting iceberg, sitting there in the middle of layers that should have been undisturbed deep water, looking exactly as wrong as they were. He stood there for a long time, because if the magnetic data was right, and the glacial evidence was right, and both of them were pointing at the same conclusion, then something had happened to this planet that the science of his time had no comfortable framework to contain. Not an ice age. Ice ages are regional. Ice ages leave refuges. Ice ages end because the planet's own rhythms bring them to an end. In thousands of years, in tens of thousands, in the slow tilting of an axis and the cycling of an orbit. What the rock in Namibia was suggesting was something else entirely. It was suggesting something close to the impossible, that ice had reached so far across this planet that Earth itself had become something close to a frozen world. That 700 million years ago, ice had not stayed in the high latitudes where ice belongs. It had moved south and north simultaneously, from both poles toward the middle of the world, until it reached places that today sit under tropical sun and warm ocean water. And if that was true, then everything alive on this planet at that moment had been pushed into whatever small and marginal places remained, into the dark, into the cold, into the edges of a world that had turned, for reasons that were not yet clear, almost completely against life. The question that follows from that is not a geological question. It is not a question about sediment or isotopes or the ancient behavior of magnetic minerals in cooling rock. It is the question this story is going to follow. If Earth nearly froze from pole to equator, how did life survive long enough for us to exist? Before the ice, there was a sea. Not the sea you know. Not blue in the way that photographs make oceans look blue. Not loud, with the sound of waves breaking on a shore lined with trees. This sea had no trees on its shore. It had no shore in the way we would recognize one. The land that edged it was bare rock, dark and silent, swept by wind that had nothing to slow it down, nothing to bend, nothing to move through except more bare rock and the open sky above it. But the sea itself, the sea was alive, not visibly, not in any way that would have meant anything to a pair of human eyes. Had human eyes existed to look at it, which they did not, and would not for another 700 million years, you could have stood at the edge of that ancient ocean and seen nothing but water, sunlight on the surface, gentle movement, the ordinary appearance of a world at rest, but the water was full. In the upper layers, where sunlight reached, cyanobacteria drifted and divided and drifted again. They had been doing this for more than 2 billion years before this moment. They were, in every meaningful sense, the most successful living things the planet had ever produced. They required almost nothing: light, water, a handful of dissolved minerals. And in exchange, they did something that would turn out to matter more than almost anything else in the history of this planet. They took carbon dioxide from the water and the air above it, and they released oxygen. Slowly, invisibly, without intention or awareness of what they were doing, they were, in the only way that counts, running the world. Below the sunlit surface, in the middle depths, where light grew thin and then vanished, other things lived. Bacteria that did not need light at all, organisms that fed on what fell from above. The bodies of the dead drifting down through the dark water column in a slow and continuous rain of organic material. A whole ecology of things that had never seen the sun and had no need of it, living in the cold and the pressure and the chemistry of deep water, and on the seafloor, in the warm shallows near the ancient coastlines. Microbial mats spread across the rock in thin and intricate sheets, layers of different organisms living on top of each other, each one processing what the one above it left behind, building structures that would have looked, to any observer capable of appreciating them, like the most delicate and complex things in existence, which they were, because at this point in the history of life, they were nearly everything. This is the world we need to hold on to before the story moves forward. Not because it was simple. It was not simple. The chemistry of that ancient ocean was more active and more varied than anything a glance at its empty surface would suggest. Carbon cycles ran through it. Sulfur cycles. Nitrogen cycles. The water itself was a medium of constant exchange between living things and their environment, each taking what it needed and releasing what it did not, in a web of chemical transactions that had been running and refining itself for billions of years. It was a world that worked, and it was a world with something at stake, not in the way that a world with animals and forests and the slow green weight of life on land has something at stake, but in its own way, on its own terms. This ocean had built something real. Time, patience, 2 billion years of chemistry finding its way toward arrangements that functioned, that persisted, that passed something forward to whatever came next. The cyanobacteria did not know they were part of a project. Nothing in the ocean knew, but the project was real nonetheless, written in the oxygen accumulating in the atmosphere above and in the organic carbon settling into the sediment below. There was warmth here that had been earned. There was also a particular quality to the light in the upper ocean, a quality that would have been invisible to any eye that did not exist to see it. But that was real in the only sense that matters for physics, which is that it was doing something, photons arriving from the sun, entering the water, being absorbed by pigments in the cyanobacteria, driving the chemical reactions that turned carbon dioxide and water into sugar and oxygen. This had been happening for more than 2 billion years. It was as ordinary in this world as breathing is in ours. It was also, though nothing in the ocean had any way of knowing this, about to become very difficult to do. Now look at the land. The supercontinent that geologists call Rodinia was breaking apart. This had been happening for millions of years before the moment we are standing in, and it would continue for millions of years after, as it pulled itself apart along deep fractures in the crust. It created new coastlines where there had been interior rock. Imagine the edge of a continent opening like a slow wound over millions of years. exposing fresh rock to rain and wind and the chemical work of weathering. New rivers forming along those edges, carrying dissolved minerals down to the sea. New shallow bays filling with sediment from the newly eroded land. A coastline that did not exist a million years ago, now wet and exposed and reacting with the rain falling on it. This matters more than it might seem. When rain falls on exposed silicate rock and begins the slow work of breaking it down, it pulls carbon dioxide out of the air. The carbon combines with minerals from the rock, gets carried by rivers to the sea, and eventually settles into sediment on the seafloor, locked away from the atmosphere for millions of years. This is one of the planet's oldest thermostat mechanisms, a way of drawing down atmospheric carbon dioxide over geological time, cooling the planet when it runs warm, nudging the system back toward balance. Rodinia's breakup meant more coastline, more exposed rock, more freshly opened surfaces for rain to fall on, more carbon dioxide being pulled from the atmosphere and sent to the seafloor in the minerals carried by the new rivers. In a stable system, with a brighter sun and higher baseline carbon dioxide, this would have been absorbed. Volcanic activity would have released carbon elsewhere. The ocean would have cycled it back. The planet would have found its equilibrium, the way it always had. Slowly, across millions of years, without crisis. But the world was not quite in a stable system. The sun, 700 million years ago, was slightly fainter than it is today. The young sun gave off less energy than it does now, which meant Earth needed more greenhouse warming just to maintain the temperatures that the ocean's life had organized itself around. And now, with Rodinia pulling apart and new coastlines forming faster than volcanism could compensate, atmospheric carbon dioxide was being drawn down further than it had been in a very long time. The ocean did not know this. The cyanobacteria did not know this. The microbial mats on the sea floor in the warm shallows did not know this. They had no mechanism for knowing anything beyond the chemistry of the water immediately around them. They continued doing what they had always done, dividing, drifting, processing the minerals they needed, releasing the oxygen they did not. The light still reached the upper ocean. The water was still warm in the shallows near the coast. The ancient chemical transactions were still running, still finding their way through their cycles, still building the invisible architecture of a living planet, one molecule at a time. And yet, there was a condition in that world, a particular arrangement of light and warmth and chemistry and living things doing their quiet work in the sunlit water, that would not come again in quite the same form. Not because it was precious, not because the universe was paying attention to it, but because the forces quietly rearranging the planet's chemistry were not going to stop. And the world those forces were building toward was one that the life in that ancient warm sea had never encountered before. Not in any form, not in any version that its biology had developed any response to. The warmth in that shallow ocean was real. It had been real for a very long time. It was almost over. Not today. Not in any single season or year or century. But in the time that geology measures, in the slow accumulation of change across millions of years, the conditions that had made that ocean what it was were beginning, almost imperceptibly, to shift in a direction that only the rock record would eventually be able to describe. Something was coming that the sea had no name for. That had no name at all. Yet, here is something true about ice that is easy to forget. Ice is white. That sounds like the beginning of a children's book. Not a story about planetary catastrophe, but stay with it for a moment. Because the color of ice is where everything starts, and where the logic of what happened to this planet 700 million years ago becomes, once you see it clearly, almost unbearably simple. White surfaces reflect light. Dark surfaces absorb it. You have felt it yourself. Standing on dark pavement in summer versus standing on a lighter surface nearby. The pavement holds heat. The difference is the color. And the difference in temperature between the two surfaces on a hot afternoon is not subtle. Now, scale that up. When ice forms on the surface of an ocean, it replaces dark water with white ice. Dark water absorbs roughly 90% of the sunlight that hits it, converting that energy to heat, warming the surface and the air above it. Ice reflects most of that same energy back into space, unused. The difference between those two numbers, multiplied across thousands of square kilometers of ocean surface, is an enormous amount of energy. Energy that was previously warming the planet is now being returned to space, as if the planet had decided it did not need it. The planet receives less heat. The planet cools. When the planet cools, more ice forms. When more ice forms, more sunlight is reflected. When more sunlight is reflected, the planet cools further. You can already see where this is going. What you are looking at is not a cycle in the sense that the word is usually meant, not something that goes around and comes back to where it started and maintains a steady state. What you are looking at is an amplifier. Each step does not return the system to its starting point. Each step makes the next step larger. The more ice there is, the more the planet cools. The more the planet cools, the more ice forms. The signal does not complete a loop. It builds. Scientists call this a positive feedback. The word positive does not mean good. It means self-reinforcing. It means the system is pushing in one direction with increasing force. And the further it goes, the harder it pushes. And the harder it pushes, the further it goes. In the world of 700 million years ago, with Rodinia breaking apart and carbon dioxide levels falling and the sun slightly fainter than it is today, the conditions for this feedback to take hold were assembling themselves with the slow patience of geological time. No single event caused it. No single year was the year it began. There was just the accumulation of small changes, each one unremarkable on its own. The carbon dioxide, a little lower this million years than the last. The ice, a little further south this century than the one before, until the system reached a point where the feedback became the dominant force in the planet's climate, and nothing else had the power to stop it. And then the ice began to move. It started at the poles, as ice always does. The high latitudes are colder. They receive sunlight at a lower angle, spread over a larger area, carrying less energy per unit of surface. They are the places where ice forms first and melts last in any cooling climate. In earlier cold periods in Earth's history, the ice had grown in the high latitudes and stopped. The planet's thermostat had caught it. Warmer temperatures closer to the equator had limited how far the ice could advance. And eventually the system had found a new balance. Cold, but not catastrophically so. But this time, something was different. The carbon dioxide that would normally have provided enough greenhouse warming to stop the ice at the high latitudes was not there in sufficient quantity. The weathering of Rodinia's new coastlines had drawn it down too far. And so, as the ice grew southward and northward, and the albedo feedback kicked in, and the planet began cooling faster than it had cooled in a very long time, the mechanism that had always stopped the ice before was weaker than it had ever been. The ice kept moving. Now introduce a detail that makes this story considerably more frightening. There is a latitude. somewhere between 30 and 40 degrees from the equator, that climate models identify as a critical range. In many Snowball Earth models, if ice advances past this point, the system may have no easy, stable intermediate state. The ice is now covering enough of the planet's surface that the reflective effect begins to overwhelm the remaining ability of the warmer ocean to compensate. The system tips, and in the hard Snowball version of this story, once it tips, the ice does not stop at some comfortable middle latitude and hold there. It may keep going until it reaches the tropics, and then the equator, and then everywhere. This is what the dropstones are telling us. Those individual boulders, dropped from the bellies of melting icebergs into fine ocean sediment that had been accumulating undisturbed on seafloors that the magnetic record places near the ancient tropics, did not get there by any mechanism other than ice. A boulder does not travel through open water. A boulder does not arrive in the middle of fine, deep water sediment by any process except being frozen into an iceberg, carried out over the ocean, and released when the ice around it melted. When you find a boulder sitting in the middle of undisturbed fine sediment, you are looking at direct physical evidence of ice in that location. They appear in the geological record of this period on every continent, in sediment layers that should never have seen ice, in latitudes that, by every available measure of ancient geography, were tropical. They are the fingerprints of ice in places where ice should not have been able to reach. And below those dropstone layers, in many sections around the world, are the last traces of the warm, shallow ocean that came before. The microbial mats, the carbonate sediments built by organisms living in sunlit water, the chemical signatures of a functioning, living, warm marine environment, and then the dropstones, and then something that looks, in the rock record, like a silence. The planet had a trap built into its climate system, a trap that was very difficult to fall into under normal conditions, because normal conditions included enough greenhouse gas and enough solar energy to keep the ice safely away from that critical latitude. But under the specific conditions of 700 million years ago, with carbon dioxide depleted by the weathering of Rodinia's new coastlines and the sun slightly fainter than it is today, the trap was closer than it had ever been. And life had no way of knowing. The cyanobacteria in the upper ocean had no way of detecting the slow advance of ice thousands of kilometers away. The microbial mats in the warm shallows had no sensory apparatus that could register the slight cooling of the water over centuries and millennia. No capacity to understand what that cooling meant on a planetary scale. No mechanism for responding to it in any way beyond the immediate chemistry of their immediate environment. They continued what they were doing, which was the only thing they could do. The trap closed, and somewhere in the remaining water, in whatever spaces the ice had not yet reached or had not yet frozen solid, the living things that had built that warm ancient ocean over billions of years were now in a world they had never encountered. A world their biology had no memory of, no preparation for, no evolved response to. The warmth that the first chapter described was gone. What replaced it was something the planet had not experienced at this scale in the entire history of early complex life. And it would not end quickly. That is the thing that matters most, and the thing that is hardest to hold on to as the story moves forward into what came next. It would not end quickly. There is a number that appears in descriptions of Snowball Earth that is worth sitting with before we go any further. Not because the number is precise. It is not. The honest answer is that we do not know exactly how long the ice lasted, and the estimates vary considerably depending on which glaciation you are measuring and which proxy evidence you are using to measure it. The number shifts between papers, between research groups, between the different techniques that scientists use to read a past that left no witnesses and no direct records. But the range of the estimates is itself the thing that matters. Tens of millions of years. Not thousands, not hundreds of thousands. Tens of millions of years of ice holding the surface of this planet, covering the ocean and the land and everything that lived in the thin strip of environment between them, holding it all under a condition that the biology of the time had no framework for and no response to. Try to feel that number rather than understand it. The story of tool-making hominins reaches back roughly 3 million years. Every stone tool, every campfire, every human hand that shaped something for a purpose, all of it fits inside 3 million years. Recorded human civilization, the cities, and the writing, and the mathematics, and the accumulated knowledge of everything our species has figured out and written down, reaches back only a few thousand years. Both of those spans vanish inside the timescale of the snowball. The ice lasted longer than the entire history of human tool use, multiplied by many times over. The dinosaurs went extinct 66 million years ago. The ice that covered this planet 700 million years ago lasted, in some estimates, for a span of time that represents a significant fraction of that entire interval. This is the thing about deep time that the human mind keeps bouncing off of. We can say the numbers. We can write them down. We can nod at them in the way that you nod at something you have registered without actually absorbing. But to feel what tens of millions of years of ice actually means, to feel it in the way that the story needs you to feel it, requires a different kind of effort. So, try this. Imagine a winter that does not end. Not a metaphorical winter, a real one. Ice on the ground, cold in the air, the particular quality of light in a sky that has no warmth in it. The way your breath becomes visible the moment it leaves your mouth. The way everything familiar becomes slightly harder in the cold. Now imagine that winter lasting through the following spring, which does not come, through the following summer, which does not arrive, through the following year, and the year after that, and the year after that. Imagine it lasting through your entire lifetime without a single morning where the air smells like something is thawing, without a single afternoon where the light has that particular low angle that means warmth is on its way, without a single season that is anything other than what winter is. Now imagine it lasting through your children's lifetimes, and their children's, and 100 generations after that, and 1,000, and 10,000. And you have not yet covered the first million years. The ice did not come and go in a season. It did not cycle in and out the way the ice ages of the more recent past have done, with their rhythms of advance and retreat tied to the wobble of the Earth's orbit and the tilt of its axis. Those ice ages, the ones that shaped the landscape of the Northern Hemisphere in the last 2 million years, the ones that carved the Great Lakes and pushed glaciers down through what is now Manhattan and buried much of northern Europe under ice sheets kilometers thick. Those lasted tens of thousands of years at their longest and felt immense to the ecosystems that lived through them. They were nothing compared to this. What the snowball Earth glaciations represent is ice not as a phase the planet was passing through, not as a temporary excursion from a warmer baseline that the climate would eventually return to, but as a state, a condition the planet had settled into and could not leave by any of the normal mechanisms. The thermostat that had always kept the ice at bay in the high latitudes had been overwhelmed. The feedbacks that would normally have brought the system back toward balance were locked out by the same ice that had created the problem. Every process that would have removed the ice under normal conditions was either stopped or severely hampered by the ice itself. And then it stayed. Those 4 words deserve their own moment before we continue. And then it stayed. Because that is the thing about the snowball that does not fit the narrative frameworks we usually reach for when we try to make sense of catastrophe. We expect catastrophes to have a shape, a beginning, a peak, an end. We expect them to be survivable in the temporal sense, to be events that pass and leave a changed but recovering world in their wake. A hurricane reaches maximum intensity and then weakens as it moves over cooler water or over land. A volcanic eruption sends its column into the sky and then quiets. Even the extinction of the dinosaurs, the event that defines mass catastrophe in the popular imagination, happened within a geologically brief interval. Something struck. The world changed. Things died. And then, across millions of years, something else began. Snowball Earth did not work like that. There was no peak followed by resolution. There was the trap closing. And then there was the trap staying closed. In a stillness that had no precedent in the history of life on this planet and would have no parallel after it. Picture the surface of the planet during this time. The ocean, which had been the center of everything alive on Earth for more than 3 billion years, was covered not by a thin skim of winter ice that would melt in a few months, by ice sheets that in many regions may have extended hundreds of meters in depth, grinding slowly under their own weight, carrying rock embedded in their bellies, scoring and scraping the seafloor sediments beneath them as they moved. The ocean surface, which had received sunlight for billions of years and converted that light into the chemistry of life, was sealed away beneath a lid that let almost none of that light through. The equatorial regions, which receive the most solar energy of anywhere on the planet, may have had thinner ice in some models. There are researchers who argue for small areas of open water near the equator, refuges of liquid surface ocean maintained by the concentration of solar energy at low latitudes. Others argue the ice was nearly as thick and complete at the equator as anywhere else. We do not know. What we know is that even in the most optimistic version of the snowball, the warm, shallow tropical seas that had hosted the flourishing microbial communities of the previous chapter were gone, replaced by ice, or by conditions so close to the edge of survivability that they were nearly indistinguishable from gone. The surface of the planet, seen from space, would have been white. Not the blue marble, not the brown and green of continents with their soils and their vegetation. White, from pole to pole, broken only by the dark rock of volcanic mountains pushing through the ice, and by the occasional eruption that punched through the frozen surface and sent a column of gas and ash into an atmosphere that had almost nothing breathing it. It was a different planet. The wind still moved across the ice surface, driven by the temperature differences between equator and poles that persisted even in a frozen world. The planet still rotated. The sun still rose and set, its light falling on white ice and bouncing back into space, warming nothing, feeding nothing, doing none of the work it had been doing for billions of years in the sunlit ocean below. The volcanic vents along the mid-ocean ridges still emitted their heat and chemistry into the water below the ice. The deep ocean, insulated from the frozen surface by its own depth and by the geothermal heat rising from the mantle below, remained liquid, cold, dark, under enormous pressure, but liquid. And in the rock record of the carbon isotopes laid down during this period, There is a signal that scientists have spent decades learning to read: the carbon isotope excursions of the Cryogenian period, the geological name for this chapter of Earth history, are among the largest and most anomalous in the entire record of Earth's chemistry. They are a long distortion in the planet's chemical memory, preserved in stone across hundreds of millions of years, telling anyone who knows how to read it that something was deeply wrong with the carbon cycle for a very long time. A record of a system running in a mode it had never run before and has never run since. The ice came, and then it stayed. Not for a winter, not for a century, not for the lifetime of a species, or a genus, or a family, or an order, for millions of years. In some versions of this story, for tens of millions, in a cold and a darkness and a stillness that had no name, because there was nothing alive on the surface of this planet capable of naming anything. The question that all of this has been building toward, the question the cold open asked, and that this chapter has been preparing the ground for, is the one that follows from every word of what has just been described. In all of that ice and time and cold and dark, where was the life? The first thing to understand is that life did not fight back. There was no resistance, no adaptation that emerged in time to meet the crisis, no evolutionary response that spread through a population fast enough to matter against what was happening, no version of survival that involved anything recognizable as struggle or will or the decision to continue. The organisms alive when the ice closed over the surface of this planet had no mechanism for understanding what was happening to them. They had no nervous systems capable of registering cold as a threat to be avoided. They had no behavior that could be redirected toward survival in any meaningful sense. They had no awareness at all, in any form that the word awareness has ever been used to describe. They simply continued, or they did not. And the ones that continued did so not because they were stronger or more adaptable or better suited to what was coming. They continued because they happened to be in places where continuing was still possible, where the specific chemistry of their immediate environment had not yet crossed the threshold beyond which their particular way of processing energy stopped working, where the temperature was still within the range their enzymes could function in, where there was still enough of whatever they needed, whether light or chemical energy or liquid water, to keep the reactions running. That is not heroism. It is just the brute, impersonal geometry of where things were when the trap closed. But it is enough. It turns out to be exactly enough. And the places where it was still possible to continue are worth understanding, because they are the only reason this story has anything more to say. Start at the bottom of the ocean. In the deep sea, along the boundaries where tectonic plates pull apart and the mantle is exposed to the water above, there are vents, cracks in the seafloor through which superheated water emerges, carrying dissolved minerals and chemicals from deep within the earth. The water immediately around these vents is warm, sometimes extremely warm. In an environment where the surrounding deep ocean is near freezing, and the chemistry that comes up with that water, hydrogen sulfide, methane, dissolved iron and manganese and other reduced compounds, is a source of energy for organisms that have no use for sunlight and never have. These organisms, the chemolithotrophs, the life that runs its metabolism on the energy stored in rock chemistry rather than on the energy of the sun, had been present in the deep ocean long before the Snowball arrived. They were not a new invention. They were an ancient and already well-established way of being alive, completely independent of what was happening at the surface, completely indifferent to whether light was reaching the upper ocean or not. When the ice closed over the ocean above them, nothing changed for these organisms in any immediate or meaningful sense. The vent chemistry continued. The hot water continued to flow. The minerals continued to emerge from the sea floor. The organisms continued to process those minerals and release the waste products of their metabolism into the cold water around them. They did not know the surface was frozen. They had no way of knowing. The ice was kilometers above them, in a world they had never had any connection to, and would never have any connection to. Separated from their environment by the enormous insulating depth of the ocean itself. For them, nothing had changed. This matters in a way that is easy to underestimate. It means that even in the most extreme version of the snowball, even if the ice extended to the equator and covered the ocean surface completely and cut the sunlit zone off entirely from photosynthesis, there was a portion of the biosphere that continued without interruption. Small, isolated, in the dark, at the bottom of a frozen ocean, but continuous. Now move upward through the water column, above the hydrothermal vents, in the cold and the dark of the intermediate depths. The water was liquid. The snowball did not freeze the ocean solid from top to bottom. The ice was a surface phenomenon, thick and grinding and persistent at the top. But the physics of geothermal heat rising from below and the insulating mass of deep water above the vents meant that below a certain depth, liquid water remained throughout the snowball's duration. Cold, liquid water. Dark, liquid water. Water under enormous pressure with very little energy flowing through it. But liquid. And in liquid water, even cold, dark, liquid water with minimal energy inputs, certain kinds of life can persist. Organisms with very low metabolic requirements, things that can reduce their processing to a near standstill, running the minimum possible chemistry to stay alive. Waiting in a state that is not quite dormancy, but is not vigorous activity either. Things that can live on the sparse chemical energy filtering down from the vents below and the minimal organic material drifting down from above, on whatever trickle of sustenance a mostly frozen world provides to its depths. They were not thriving. Thriving was not available, but they were present. Their chemistry still running at the lowest possible level, that still counts as running. Now consider the ice itself, which is the part of the story that surprises people most when they first encounter it. In the near equatorial regions, where the angle of the sun was highest and the solar energy input was greatest, some climate models suggest that the ice may have been thinner than at higher latitudes. And ice, when it is thin enough and clear enough, is not perfectly opaque. Light can penetrate it, not the full, rich sunlight of an open tropical ocean. Something much reduced, a fraction of the light that reached the surface, filtered and scattered by the ice above, arriving at the underside as a dim and diffuse illumination that would have looked to a human eye like almost nothing. But almost nothing is not nothing. And photosynthesis, the process that cyanobacteria had been running for more than 2 billion years before the snowball arrived, can operate in very low light conditions. Some photosynthetic organisms are adapted to the dim conditions of deep, clear water. Some can extract what they need from light levels far below what would be needed to drive vigorous growth. In the thin ice regions near the equator, in whatever areas the ice was clear enough and thin enough to let some light through, there may have been communities of photosynthetic organisms clinging to the underside of the ice, living in conditions that were almost impossibly difficult, extracting what they could from the faint illumination above them and the cold water below. We do not know for certain that this happened, The honest position is that it is a plausible hypothesis, with some evidence in its favor and some evidence against it. And the question of exactly how much light reached the under-ice ocean in equatorial regions during the Snowball, and exactly what lived there, if anything, is not yet resolved. But we know that photosynthetic life survived the Snowball. We know that because it is here now, and tracing its lineages backward leads to ancestors that predate the ice. Something continuous with what existed before the Snowball carried photosynthesis through. The how is the question. That is the fact. And then there were the volcanic margins. In certain coastal regions, and particularly in areas of active volcanism, where the heat of the Earth's interior was close enough to the surface to matter, the ice may not have been as thick or as uniform as it was across the open ocean. Geothermal heat can melt ice from below. In regions where the seafloor was close enough to a volcanic heat source, pockets of warmer water may have persisted under thinner ice, or, in some cases, in open water that the volcanic heat kept from freezing entirely. Small areas, localized, marginal in every sense of the word, but present. It was not that life had no place at all. If that had been true, the story would have ended there, in the ice, 700 million years ago. And everything that came after, the Ediacaran organisms, the Cambrian animals, the fish and the forests and the dinosaurs and us, none of it would have happened. The story would have ended, and there would have been no one to tell it or to wonder how it had gone. It was that the places left were smaller than anything life had known before. Stranger, darker, further from the surface and the light and the warmth that the warm, shallow ocean of the previous chapter had offered in abundance. The margins, in the most precise sense of the word. The thin edge between conditions that could sustain a metabolism and conditions that could not. Life retreated to that edge and persisted there, not because it chose to or understood that it needed to, but because retreating was what the physics of its situation required, and because enough of it happened to be in the right places when the trap closed. There is something in this that resists the emotional categories we usually reach for. It is not heroism. It is not endurance in the sense of something that requires will. It is not tragedy in the clean sense, because tragedy requires awareness of what is being lost. And there was no awareness. What life was doing in the margins of the Snowball was not effortful. It was just happening, in the way that chemistry always happens, because the conditions for it to happen still existed in just enough places for the thread to continue. But the thread continued. In the dark water above the hydrothermal vents, in the cold intermediate depths where organisms with minimal metabolic requirements kept their chemistry running at near standstill, in the possible under-ice communities near the equator where the faintest photosynthesis may have kept going, in light levels that were almost nothing, in the volcanic pockets along icy coastlines where geothermal heat created small exceptions to the general rule of frozen. In all of these places, in all of these marginal and unlikely and barely sufficient spaces, something kept processing energy, something kept dividing, something kept doing the only thing life has ever done, which is to continue until the conditions for continuing no longer exist, for millions of years, perhaps for tens of millions. The conditions for continuing still existed, just barely, in just enough places. And that is why there is a chapter 5. Not because the ice relented out of some kind of geological mercy, not because something intervened on life's behalf or decided that what had happened was enough. The ice did not relent because life needed it to. The ice relented for reasons that had nothing to do with life at all, for reasons that were as impersonal and as indifferent as the reasons it had formed in the first place. But it did relent. Eventually, no one came. That is the first thing to say about how the Snowball Earth ended. Because the temptation in any story about a crisis, this large and this long, is to look for the thing that arrived and fixed it. The intervention. The turning point. The moment when something from outside the system reached in and changed the conditions that had been holding the planet in its frozen state for tens of millions of years. There was no such moment. What ended the Snowball Earth was not an intervention. It was not a rescue. It was an accumulation. A slow, unintentional, completely impersonal build-up of something that had been happening all along. Beneath the ice and below the frozen surface and in the cold atmosphere above, unnoticed by anything, changing nothing that was immediately apparent, accumulating toward a threshold that it would eventually cross in a way that owed nothing to intention and everything to arithmetic. To understand it, go back to something that was mentioned briefly in the second chapter and left there without full explanation. Go back to volcanoes. Not the dramatic kind. Not the kind that makes news and fills the sky with ash and sends a column of fire and rock high enough that it shows up on satellite imagery from the other side of the planet. Not Pinatubo or Krakatoa or the caldera forming eruptions that reshape landscapes in hours and drive regional cooling for years. What we need to think about here is the quiet kind. The kind that is always happening. Everywhere. All the time. At the bottom of the ocean and along the edges of continents and in the slow seepage of gases through volcanic rock that has been doing this for billions of years without anyone paying particular attention to it. Volcanoes are driven by the heat of the Earth's interior. That heat has been present since the planet formed, generated by the decay of radioactive elements in the rock and by the residual warmth of formation itself. And it has been finding its way to the surface ever since, driving the slow convection of the mantle, powering the movement of tectonic plates, expressing itself at the surface as volcanic activity of various scales and kinds. This process does not respond to what is happening at the surface. The volcanoes do not know there is ice above them. The magma rising through the crust does not alter its behavior because the ocean is frozen. The outgassing of the mid-ocean ridges, where plates pull apart and new seafloor is created in a continuous process that has been running for billions of years, does not stop because the planet has entered a snowball state. The volcanoes continued. They had no choice. They were doing what the physics of the planet's interior required. And the physics of the planet's interior did not care about the ice. And one of the things they released, along with water vapor and sulfur dioxide and various other compounds, was carbon dioxide. Carbon dioxide is a greenhouse gas. More carbon dioxide in the atmosphere means more heat retained at the surface. This is not complicated in its basic form. What matters here is not the mechanism, but the bookkeeping under normal conditions. The carbon dioxide that volcanoes put into the atmosphere does not stay there indefinitely. It is removed through a process called silicate weathering. Rain falls on exposed rock. The carbon dioxide dissolved in the rainwater reacts with the silicate minerals in the rock, and the products of that reaction eventually make their way to the ocean and are buried in seafloor sediment, locking the carbon away from the atmosphere for millions of years. This is the planet's long-term carbon cycle, the system that has regulated atmospheric carbon dioxide and surface temperatures across geological time. Volcanoes put carbon in. Weathering takes it out. The balance between those two processes, running across millions of years, determines how warm or cold the planet runs. Now, Think about what happens to the weathering side of this system when the planet is covered in ice. It nearly stops. Weathering requires liquid water falling on exposed rock. It requires rain. When the land is buried under ice sheets and the ocean surface is frozen over and the hydrological cycle, the evaporation and precipitation that drives weather, has been dramatically reduced by the cold, the weathering of silicate rock slows to a tiny fraction of its normal rate. There is almost no rain falling on exposed rock, because there is almost no exposed rock. And because there is almost no rain, the mechanism that removes carbon dioxide from the atmosphere has been shut down by the very conditions that the carbon dioxide would help to remedy. But the volcanic side of the system keeps running. Carbon dioxide rises from the vents and the ridges and the seeps along continental margins, enters the atmosphere, and stays there, because there is almost nothing to remove it. Here is the thing that stopped me when I first sat with this clearly. This is not a rescue. There is no geological mercy operating here. No version of the planet noticing what has happened to it and deciding to undo it. It is just two processes continuing to run. One of them has been nearly switched off by the ice. The other has not. The outcome is not designed. It is arithmetic. Carbon dioxide goes in. Almost none comes out. The concentration rise very slowly, over millions of years, one molecule at a time, building in an atmosphere above a frozen world that gives no sign that anything is changing, that looks from the outside exactly as white and cold and sealed as it did 1,000,000 years before and 1,000,000 years before that. Not a rescue, an accumulation. The carbon dioxide builds in the atmosphere of a frozen planet, year after year, century after century, millennium after millennium, while beneath the ice and in the deep ocean and in the marginal spaces where the thread of life is being held by organisms that do not know they are holding it. The slow chemistry of survival continues at its minimal pace, indifferent to what is building above. At some point, after enough millions of years of volcanic outgassing into an atmosphere that has almost no weathering sink to remove it, the carbon dioxide concentration reaches a level where the greenhouse warming it provides begins to compete seriously with the cooling that the ice's reflectivity is driving. The numbers begin to shift. The planet is still white, still reflecting most of the sunlight that hits it. But now the atmosphere above the ice is thick enough with carbon dioxide that the heat trying to escape from the surface is being trapped and redirected back downward in increasing quantities. The surface temperature begins, very slightly, to rise. Not dramatically, not in any way that would register as change from year to year, or even from century to century. But the balance is shifting. The ice that has been maintaining itself, losing as much to slow sublimation and marginal melting as it gains from the minimal precipitation of a frozen world, begins to tip in the direction of net loss. The margin retreats, slightly, in the equatorial regions where the solar energy is highest and where the balance was already closest to the edge. Where the ice retreats, dark ocean surface is exposed, and dark ocean surface absorbs heat, and absorbed heat warms the surface slightly more, and a slightly warmer surface causes slightly more ice to melt. The same logic that locked the planet into the snowball is now running in reverse. The albedo feedback that drove the ice toward the equator is now driving the ice toward the poles. Not because anything has changed, except the direction. Each small retreat exposes dark ocean. Each bit of dark ocean absorbs heat. Each bit of absorbed heat warms things slightly further. the signal is building. But now it is building in the direction of warmth instead of cold. The planet, slowly, is beginning to come back to itself. Not because it was saved, not because life demanded a reprieve, because the arithmetic of the carbon cycle, running its slow and indifferent calculation across tens of millions of years, had finally reached the number that changed what was possible. The volcanoes did not know what they had done. The carbon dioxide did not know what it had done. The ice did not know it was retreating. None of it knew anything, because none of it was the kind of thing that knows. It was just geology, just the slow machinery of a planet operating according to the same principles it had always operated according to. Indifferent to the life sheltering in its margins, and equally indifferent to the transformation it was about to deliver. Not a rescue. An accumulation that became, over enough time, something that looked from the outside exactly like one. The ice broke. Not gently. Not in the way that winter ends in a temperate climate. With a slow warming and a gradual retreat, and the quiet arrival of something that feels like relief. The Snowball Earth did not end the way a difficult season ends. It ended the way a vessel ends, when the pressure inside it finally exceeds what the walls can hold. It ended fast. And what came out was not spring. To understand why, hold two things in your mind simultaneously. The first is the ice. Tens of millions of years of it. A planet wrapped in white, reflecting nearly everything the sun sent toward it, back into space. Running cold and still and sealed. Its chemistry locked into a mode that had no precedent and would have no repetition in the history of life. The second is the atmosphere above that ice. Tens of millions of years of volcanic carbon dioxide with almost nowhere to go. Building. Accumulating, molecule by molecule, century by century, in an atmosphere that had almost no weathering sink to remove it because the ice had covered the rock and suppressed the rain cycle into something barely functional. By the time the threshold was reached, by the time the carbon dioxide had built to levels sufficient to begin tipping the albedo feedback into reverse, the atmosphere of the Snowball Earth contained a concentration of greenhouse gas that had no parallel in the planet's recent history. And then the ice began to melt. The retreat of the ice changes the weathering equation, as ice pulls back and exposes rock, and as rain begins to fall again on those exposed surfaces. Weathering resumes. Carbon dioxide starts to come out of the atmosphere through the same silicate weathering that had been nearly shut down for millions of years. But the weathering cannot accelerate fast enough to keep pace with what is happening. The carbon dioxide in the atmosphere is not slightly elevated. It is enormous. By any standard, the planet had experienced since before complex life existed, and the feedback loop running the deglaciation is now compounding. Each bit of retreating ice exposes dark ocean. Each dark ocean surface absorbs heat. Each absorbed unit of heat retreats the ice further. Each further retreat exposes more dark ocean. The warming is accelerating faster than any removal mechanism can follow. What this means for the climate of the planet coming out of the Snowball is not a return to the conditions that existed before the ice arrived. It means an overshoot. The planet does not stabilize at the warm tropical ocean temperatures of 700 million years ago. The world described in the first chapter, with its sunlit cyanobacteria and its warm shallow seas and its quiet chemistry, the greenhouse forcing of the accumulated carbon dioxide, running into a feedback loop of accelerating deglaciation, pushes temperatures past that baseline and keeps going. Some estimates suggest the aftermath of Snowball deglaciation may have involved surface conditions that were, at least temporarily, among the warmest the planet had experienced in hundreds of millions of years. From icehouse to greenhouse, not gradually, in the context of geological time, very fast. The ocean surface, which had been sealed under ice for tens of millions of years, was now exposed to a sky thick with carbon dioxide and to sunlight that had been bouncing off white ice for all that time and was now, finally, reaching liquid water. The ocean absorbed heat rapidly. Surface temperatures climbed, and the chemistry of the seawater, which had been running in its strange snowball mode, disconnected from the atmosphere above it by the ice lid, now reconnected. The carbonate chemistry of the water shifted rapidly in ways that registered throughout the water column, changing what minerals could dissolve, what could precipitate, what the ocean's surface felt like to any organism trying to live in it. Then came something that geologists can find in the rock record at dozens of locations on every continent. Sitting directly on top of the glacial deposits of the Snowball, and marking the boundary between the frozen world and the world that followed it, with a layer of stone that has no ordinary explanation. Cap carbonates. A cap carbonate is a layer of carbonate rock, typically limestone or dolostone, that forms directly above glacial sediment in the aftermath of a snowball glaciation. They are called cap carbonates because they cap the glacial deposits, sitting right on top of the evidence of ice like a seal on a letter. They are found on every continent. They sit immediately above the dropstones and the glacially striated surfaces, and they are chemically anomalous in ways that took decades of study to begin to understand. They form fast, by geological standards, almost instantaneously. Thick layers of carbonate laid down in what the rock record suggests was a very brief interval, driven by the extraordinary chemistry of an ocean that had been locked in a frozen state for tens of millions of years, and was now suddenly exposed to a warm, carbon dioxide, saturated atmosphere, and a dramatically altered chemical environment all at once. Stand in front of one of these outcrops, and you are looking at the signature of an ocean in shock. Not recovering peacefully, not returning to normal on a gentle schedule. In shock. The chemistry of the water changing faster than it had changed in a very long time. Driven by forces that had been building for tens of millions of years and were now releasing all at once. In a geological instant, the cap carbonates are what an ocean sounds like when it finally opens after a very long silence. And what it sounds like is not quiet. Now think about what all of this meant for the life that had made it through. The hydrothermal vent communities in the deep ocean were somewhat insulated from the most dramatic aspects of the surface chemistry change. They continued in their darkness, running their chemistry on the energy of the Earth's interior, largely indifferent to what was happening in the water column above them. For them, the end of the snowball was perhaps less violent than what the surface experienced. But the organisms in the shallower refuges, the things that had been living under thin equatorial ice or in volcanic pockets near the surface, were now exposed to a world changing with a speed that had no precedent in their evolutionary experience, not the experience of any individual organism, which did not exist in any meaningful sense. The accumulated evolutionary experience of their lineages, the memory encoded in the molecules of what their ancestors had been able to tolerate. The ocean was warming, the chemistry was shifting, and the light that had been absent or barely present for tens of millions of years was suddenly flooding back into the surface ocean as the ice retreated, bringing with it the energy that photosynthesis requires. More light, more energy, more warmth, more chemical flux, all arriving at once. In a world that had been starved of all of them for an almost incomprehensible span of time. Some models suggest that nutrients, delivered by dramatically intensified weathering of the newly exposed rock, and redistributed as the ocean's circulation reorganized, may have pulsed into the newly sunlit surface ocean in concentrated bursts. If that happened, for any photosynthetic organism that had managed to persist through the snowball, it would not have been a subtle signal. It would have been an overwhelming one. Growth, expansion, the rapid colonization of a surface ocean that was suddenly open in a way it had not been for tens of millions of years. But the ocean they were expanding into was not the ocean their ancestors had retreated from. It was warmer, chemically different, still oscillating through the shock of deglaciation. Some lineages that had survived the snowball would not survive the thaw. Not because the thaw was more extreme in absolute terms than the freeze, but because the thaw arrived with a different kind of violence. The freeze had been slow, cold descending over millions of years. The trap closing gradually enough that organisms could retreat step by step into the shrinking spaces where life remained possible. The thaw was fast. The chemical environment of the ocean shifting in a geological instant in ways that some organisms were equipped to handle and others were not. The world that emerged from the snowball was not the world that had entered it. It was louder, more turbulent, chemically noisier, full of the kind of instability that accumulates when a system is held in a constrained state for a very long time and then suddenly released. Full of energy that had been building for millions of years with nowhere to go. It was a world that its own catastrophe had opened into something new. Not better, not worse. New. The organisms that made it through the freeze and then made it through the violent thaw were not what they had been before the snowball. They were their descendants, changed by the accumulated pressure of what they had survived, carrying forward into a post-snowball world, not the warm, shallow ocean chemistry of 700 million years ago, but something that had been tested in ways life had never been tested before. The ice was gone. The world it had made from what survived was just beginning to find out what it was. Somewhere on the floor of a shallow sea, in the time after the ice, something left a mark. Not a footprint, not a burrow, not anything that required muscles or directed movement, or the kind of behavior we associate with animals that have brains and intentions, and the capacity to choose. Just a shape, a soft impression in the sediment of a seafloor that had, for the first time in tens of millions of years, light reaching it from above, an outline in the mud, the suggestion of something that had been there, had pressed its form against the sediment, and was now gone, leaving behind the minimum possible record of its presence in a world that was still, slowly and painfully, finding its new equilibrium after the most dramatic climate event in the history of early life on this planet. The shape was not large. It was not impressive in the way that a dinosaur bone is impressive, with its mass and its suggestion of power and scale. It was not even particularly clear, preserved in rock that had been through 500 million years of geological history since the moment it formed. It was just a form, an outline, the unmistakable evidence that something with a shape had existed at that location, at that moment, in that ancient sea, but it had a shape. That is the thing. That is the thing that matters, when you understand where it came from and what came before it. After more than 3 billion years of life on this planet, after all the cyanobacteria and the microbial mats and the deep ocean chemolithotrophs and the long endless dynasty of things, too small and too soft to leave any impression the naked eye could see. After all of that, here was a shape, something large enough and coherent enough and present long enough to leave a mark in the mud that survived. This is the Ediacaran world, the period that follows the cryogenian glaciations. The geological chapter that begins after the last of the Snowball ice, retreats and extends forward to the beginning of the Cambrian, is called the Ediacaran. It is named for the Ediacara Hills in South Australia, where paleontologist Martin Gleisner and his colleagues began properly documenting its characteristic fossils in the 1950s, though the fossils themselves had been noticed by others earlier without anyone quite knowing what to make of them. Since then, Ediacaran fossil sites have been found on every continent, in rocks ranging from roughly 575 million to approximately 540 million years old. And the organisms preserved in those rocks have occupied paleontologists for decades without yielding anything close to a consensus on exactly what they were or how they lived. This difficulty, this resistance to easy categorization, is itself a clue to what makes the Ediacaran important. Dickinsonia is perhaps the most discussed of the Ediacaran organisms, a flat, oval form, ribbed with a regular pattern of segments running from a central axis, found in sizes ranging from a few millimeters across to nearly 1.5 meters in the largest specimens recovered. It has been studied intensively since the 1940s. Researchers have argued about whether it was an animal, a fungus, a lichen, an alga, or something with no modern equivalent. It has no mouth that anyone has been able to identify, no gut, no obvious sensory structures. It left feeding traces in the microbial mats it moved across, evidence of a metabolism that extracted something from the organic material beneath it. But the exact mechanism remains contested. Lipid biomarkers in Dickinsonia fossils, published in 2018, suggested it may have been an animal, though this interpretation has not gone unchallenged. What Dickinsonia is, definitively, is old and large, and there. Kimberella is different in ways that matter. Smaller than the largest Dickinsonia specimens, more clearly organized along a front-to-back axis, with what appears to be a distinct anterior region and evidence in the rock of directed movement across the seafloor. Scratch marks in the sediment associated with Kimberella specimens have been interpreted as feeding traces left by some kind of scraping or rasping structure. An organism moving through the world with a direction, processing the microbial material on the seafloor in a systematic way. Something was moving with direction. Something was, in whatever chemical and physical sense applies to an organism without a nervous system as we would recognize it, choosing where to go. Hold these two forms in your mind. Dickinsonia pressing its ribbed oval shape into the sediment of an Ediacaran seafloor. Kimberella moving, however slowly and however mechanically, across the surface of a microbial mat in a direction that had a front and a back, leaving in its wake the traces of a metabolism that was doing something more organized than simply absorbing whatever diffused into contact with it. And then, remember where they came from. These organisms existed on the other side of the Snowball. Their lineages, whatever exactly those lineages were, trace back through the cryogenian to ancestors that survived the ice. The organisms in the dark water above the hydrothermal vents, the communities clinging to the underside of equatorial ice in whatever thin light made it through, the life in the volcanic pockets along frozen coastlines, the minimal chemistry running in the cold, deep water of a planet that had come as close as it has ever come to ending the experiment of complex life before that experiment had produced anything you could see. The Ediacaran organisms are what came out of the other side of all of that. Not immediately. The geological distance between the last Snowball ice and the first Ediacaran fossils is tens of millions of years. A span of time in which the world was changing in ways the fossil record of that period is not yet detailed enough to fully reveal. The connection between the cryogenian glaciations and the Ediacaran organisms, the nature of the relationship between the ice and the forms that followed it, is genuinely one of the open questions in the science of early life. Researchers debate it actively. The evidence points in different directions depending on what you look at and how you interpret it. What we can say, carefully and with the appropriate acknowledgement of what we do not know, is this: the Snowball Earth and its aftermath reorganized the chemistry of the ocean in dramatic ways. The violent deglaciation, the cap carbonate events, the pulse of weathering-derived nutrients into a newly opened surface ocean, the altered patterns of carbonate saturation and oxygen availability in the water column. All of these created conditions in the Ediacaran Ocean that were significantly different from the conditions of the pre-Snowball world. Whether those changed conditions were necessary for the evolution of the complex multicellular forms we see in the Ediacaran, or whether they accelerated something that would eventually have happened anyway under the right conditions, or whether the relationship between the ice and what followed it is more complicated and more contingent than either of those framings suggests, is a question science has not yet answered. What is not in question is the sequence. Ice, then thaw, then a world with a different chemistry. Then, in the Ediacaran, one of the first great moments in the rock record when life becomes visible at a scale the human eye can recognize without instruments. But set aside the causality question for a moment. Set aside the science of what drove what and what was necessary for what, and look at the Ediacaran world on its own terms, in the way that it presents itself to us through the rock. The sea in the Ediacaran had light again, real light, reaching the surface and penetrating into the shallows, driving photosynthesis on a scale the ocean had not seen during the Snowball. The microbial mats that had persisted through the ice had expanded, colonizing the seafloors of the shallow seas in thick, organic layers, building the biological substrate that the Ediacaran organisms lived on and moved across and pressed their shapes into. The ocean had nutrients. It had chemistry that, though still adjusting from the shock of deglaciation, was organizing itself into something that worked. It had the energetic richness of a surface ocean receiving sunlight after a very long darkness. And in it, and on the seafloor beneath it, were these forms. These impossible, strange, irreducibly weird forms that fit no modern category and belong to no living lineage. We can clearly identify and resist every attempt to make them familiar by comparing them to something we already understand. After billions of years of microbial existence, after the long Snowball and the violent thaw and the turbulent chemical reorganization of a world finding its way back to something stable, life had done something it had not done before. Not invented a new chemistry, not discovered a new energy source, not crossed some threshold in metabolic complexity. It had become visible. Large shapes in the mud, impressions that persisted, organisms big enough to leave a mark that could survive 575 million years of geological history and end up in the hands of a paleontologist who would understand, upon seeing it, that they were holding evidence of something that had not existed in the world before. Not the beginning of animals, not the invention of complexity in a single moment. Ediacaran life is not Cambrian life, and the relationship between the two is itself a subject of ongoing research and debate. But the first time this story can point to shapes in the rock that you could look at and know, without any training, that something with a body had been there. This is the payoff the Snowball story has been building toward. Not a clean payoff. Not a simple one. Not one the science has fully worked out, or that any honest account can present as a proven chain of cause and effect. But a payoff in the deeper sense, that everything in the story has been pointing at the sense in which the thread that held in the margins of the Snowball world held long enough for the world that came after to be different from the world that came before. The sense in which everything that waited in the dark, without knowing it was waiting, without knowing anything at all, waited long enough for the world to open again. The Dickinsonia, pressing its shape into the Ediacaran mud, did not know about the Snowball. It had no capacity to know. But it was there because something before it had survived what the Snowball did to this planet. And something before that. And something before that. In a chain that ran without interruption, through the dark water and the marginal spaces and the volcanic refuges and the under-ice communities, all the way back to the warm, shallow ocean of 700 million years ago. It was there because the chain held, and the mark it left in the mud is the first place in this story where that chain becomes something you can see. Not a triumph, not a victory. The ice was not an adversary, and life was not a champion. They were just the circumstances and the thing that persisted through them. In the relationship that weather has with a stone that sits in it for long enough, the stone does not win. It simply remains when the weather has moved on. Life remained. And in the Ediacaran world, for the first time, you could see it remaining. You could hold the evidence of it in your hands. You could look at the shape pressed into the ancient rock and know, in your bones, that something had been there. Something with a form, something that had existed in a world that finally, after tens of millions of years of ice and the violent chemistry of thawing and the slow reassembly of a living ocean, had room for shapes to exist in. The world had opened. Not gently, not without cost, but it had opened. And in the opening, something had left its mark. Go back to the rock face in Namibia. The same cliff, the same dark layer of sediment sitting between pale carbonate below and pale carbonate above. The same evidence of a world that froze and thawed and left its signature in stone for anyone patient enough and trained enough to read it. The same place where Paul Hoffman stood in the summer of 1998 and understood that the rock in front of him was saying something that his education insisted could not be true. He spent years defending what the rock told him. Not years of easy progress, but years of active disagreement with other scientists who examined the same evidence and reached different conclusions or doubted the scale of what he was proposing. The claim that ice had reached the tropics, that Earth had nearly frozen from pole to pole, was not a claim that the scientific community accepted quickly or without resistance. The resistance was legitimate. Extraordinary claims require extraordinary evidence, and the evidence, while compelling to those who found it convincing, was not immediately convincing to everyone who examined it. In the broad shape of the story, the rocks were pointing in the direction he thought they were pointing. The paleomagnetism that placed glacial deposits at tropical paleolatitudes, the dropstones sitting in deep water sediment that should never have seen ice, the enormous carbon isotope anomalies of the cryogenian, among the largest and most unusual in the entire geological record, reflecting a carbon cycle, running in a mode it has not repeated since. The cap carbonates sitting directly on top of glacial sediments on every continent. The chemical signature of an ocean reorganizing itself after a long confinement. These pieces of evidence, assembled by researchers working independently on different continents across different decades, converged. The planet nearly froze. Not completely, perhaps, The debate between a hard snowball, with ice extending to the equator and covering the ocean surface in its entirety, and a softer version, with thin ice, or areas of open water in equatorial regions, is a real scientific debate with real evidence on both sides. And it has not been definitively resolved. We do not know exactly how thick the ice was at the equator. We do not know exactly where life survived during the snowball, or in how many separate places, or at what population sizes. The snowball Earth hypothesis is supported by a powerful and growing convergence of evidence from multiple independent lines. And it is complicated by the genuine difficulty of reading events that happened 700 million years ago in rock, that has been through 700 million years of subsequent geological history since then. We are doing the best we can with what the rock has preserved. What we know is that life survived, because we are here. That sounds like a simple observation. It is not a simple observation. Every complex living thing on Earth today, every multicellular organism, every animal and plant and fungus traces its ancestry back through the Ediacaran and the Cryogenian and the warm pre-snowball ocean to something that made it through, not because it was special, not because it was chosen or destined or better than what did not make it through, because it was in the right place when the trap closed. And the right place turned out to be just enough, and it was still there when the ice was gone. Think about what that means. Every living thing you have ever seen, every person you have ever known, every organism that has ever done anything that the word alive can be applied to, from the most ancient bacterium to the most recently evolved mammal, is connected by an unbroken chain of generations to something that was in the margins of the snowball Earth and kept its chemistry running when almost everything around it had stopped. The chain did not break. It held in the dark water above hydrothermal vents where organisms ran their metabolism on rock chemistry, indifferent to the ice kilometers above them. It held in the cold, deep ocean where things with minimal metabolic requirements slowed themselves to near standstill and continued. It held, possibly, in the thin light beneath equatorial ice where the faintest photosynthesis may have kept going in illumination that was almost nothing. It held in the volcanic pockets along frozen coastlines where geothermal heat created small exceptions to the general rule of frozen and dead. And then the arithmetic ran its course. The volcanoes continued. The carbon dioxide accumulated. The weathering stayed suppressed. The concentration climbed. The threshold was crossed. The albedo feedback reversed. The ice retreated. The ocean reorganized itself in the violent and turbulent aftermath of a deglaciation that sent conditions swinging from one extreme toward another. The cap carbonates formed and weathered, and were eventually found by geologists who spent decades arguing about what they meant. And the Ediacaran world assembled itself from the surviving lineages and the changed chemistry, slowly, across tens of millions of years, into something that had not existed before. Something that left shapes in the mud. Something that eventually, across the long Cambrian and Ordovician and Silurian and every geological period that followed, left shapes with eyes, with bones, with the capacity to move through the world with intention. And then, much later still, shapes that looked at other shapes and wondered where they came from. That wondering is this story. The fact that the wondering is possible at all is itself the answer to the question the cold open asked. If Earth nearly froze from pole to equator, how did life survive long enough for us to exist? It survived in the margins, in the dark, in the places that were almost not enough and turned out to be just enough. It survived not because it fought or adapted or found a solution. It survived because it continued. In the only way that life continues. which is by remaining alive in a place where remaining alive is still possible, until the conditions that made that place necessary finally changed. And then it inherited the change. What does it take to wait out a frozen world? Nothing heroic, nothing intentional, nothing that required understanding or awareness or the capacity to recognize what was at stake or what was being preserved or how long it was going to take. Just the simple, stubborn persistence of chemistry that has not yet encountered the condition that stops it. That is what waited. That is what the margins held. That is what eventually, across 700 million years of subsequent history, arrived at this moment, in which a mind shaped by everything that followed the snowball can sit with these words and understand, imperfectly and incompletely, but genuinely, something about the world that made it possible. Life did not defeat the ice. It outlasted it.